Program counter, this is just an emulator breakpoint. You know, you set up a point you want the emulator to return back to you, just like a breakpoint, and then set that address and you'll get your handler called. We have two different types of memory handlers. You have a specific memory handler, and then you have more generic memory handlers. This one right here, set memory handler, is it takes a specific address. It'll only be triggered when that address is touched in the context of the emulator. So for instance, at this point, if you wanted to get execution back to your script when this address is touched, you would set it like this. And these are the high-level handlers that I just talked about for a second. But you have memory write, memory read, memory access. If you'll notice, these don't take actual addresses because they'll happen anytime memory is touched, is read, written to, and access is read or write. So we also have stack versions of that. Anytime memory on the stack is read, write, or accessed, we'll throw control back to your handler. And then heap is the same way. So anytime the heap is read, written, or accessed. And then these down here are what the different handlers will look like in their arguments. So type would be read or write for any of the access handlers. In execution, we wouldn't be able to do much without it. Execution has 3 different arguments. All of them are, you don't have to have when you're using it, but steps is how many different instructions are going to be executed. For instance, I just want to execute one instruction. I want to do 100. You just put steps and it'll go from point A to, it'll go from EIP all the way down, however many steps, and then stop execution. You can also specify start and end, and you can do all these independently of each other. If I wanted to just say execute at this address, it would set EIP and it would start emulating. And if you did end, it would start emulating until you hit that address. So, pretty straightforward. We'll talk now just a little bit about modification. Since I tried to provide ways to modify data really easily in different forms of it, we'll just cover this for a second. It allows a user to set up and modify emulator information. You have an emulator working. You may hit your handler. You want to be able to query memory. You want to be able to set it. You want to be able to pull registers, local variables, things of that nature. So I've provided these. They can be scripted and used in handlers, like I just said. All modification have a complementary fetching method. So anything you see that can set memory or set stack variables or function arguments, you can use the same thing to get them, just with the get in front. So registers in the modification spectrum. We have smart setting of registers, and what they'll do is automatically determine the size based on the name. So for instance, if you want to set AX, you don't have to specify a size. You give it data, and it'll, understand the size of that piece of data. And you can also specify a name. So for instance, if I'm in IDA, and I know that this loop and this local variable is a counter, you can name ECX at that point in the loop as your counter, and then you can query that from your script at different points. So get register counter would actually give you EAX contents, or ECXs, whichever one you set. Local variables contain function-independent storage. Local variables are set by offset from the base frame, and you can work from the base frame or the stack pointer. It depends on a different flag you set in the emulator when you create it. But if you notice, you'll pass an offset. If you're setting, you will specify the value you want to set, and then again, you can name it. So this would set EBP minus 80 to this value that we specified. And you can do this a lot to set up certain functions to execute with whatever information and data you want. So very useful. Function arguments are pretty much the same as stack variables. You can use them with the name. You add the offset and you provide the data, and then you can fetch them in the same way through offset or through the name, however you want to set it up. So pretty identical. And memory is very similar. We have set memory and get memory. Set memory takes an address, and you can arbitrarily set data if you're using strings, or if you're using, D words, you can set that to, it'll automatically figure out 4 or whatever size, and if you, alternatively like to change the size of that for whatever reason, you can specify that through a keyword argument. And then here's a couple of the output methods. Log, debug, dump context, dump stack, dump memory. All these are used to, as I say, just dump out different information from the emulator. So joining these two, I've come up with a couple of very simple but very obvious examples. 3 of these are in each environment, how to just simply execute different pieces in IDA or PyEmu or PyDebug and PE file, and then a couple that are solving or at least attempting to give an idea on how to solve some of the problems we talked about earlier in reversing. IDA Pro, our example, we utilize IDA Python. We'll map our sections to memory addresses. We'll allow the user to emulate a piece of a static binary and then use handlers to track certain mnemonics and register access. And as we saw earlier, when you're using IDA or IDA PyEmu, you'll need to map in the code section and the data section, and you'll need to set EIP, and then execute. So as you can see, just a simple example from screen EA, I believe, it'll execute down however many steps we went to. And just as a logging purpose, if you turn debug on to 2, it'll print out each instruction that gets executed. So you can see that we carried through that binary. PyDebug, our live analysis or our debugging version of using an emulator. Control can be transferred from the live debugger to the emulator. So if I set a breakpoint in a process, I hit that breakpoint, I can say, set up the emulator. I want to go from here to this point and see exactly what data is being accessed, or see how the process responds, or exactly what instructions are being executed. Real context information is used, which is a highlight of it, is as soon as that breakpoint gets hit, the context is copied, so our emulator has all the information that the real process would have, except the instructions aren't actually being executed. And this actually isn't in there right now, but I'm going to add it real soon. I didn't have much time. But as I said earlier, this context, you'd be able to take it and map it back into the real process and continue execution. Possibly a good case for exploit development. A guy that helped me beta test this a little bit is using it to, when a process crashes with invalid return pointer, he will emulate different instructions to see exactly what it would take to execute to that address on the stack. As we can see, this is the PyDebug PyEmu example. We set a handler breakpoint, and what this does is that this is our breakpoint that we're going to stop in and start emulating at. And inside of that breakpoint, if you will, the emulator, when it gets created, will just loop inside that emulator. So you have a command line way to just keep stepping the emulator like you would single step a debugger. And that allows you to get all the registers each time it executes an instruction. You can query memory and things of that nature. And this is just the continuation of that. And here's it ran from the command line on calc.exe. And you'll see it attaches, hits a breakpoint, and then we'll start emulating. And then you can see the register. There's actually different ways you can dump all the registers. There's one that looks like WinDebug, and then there's this one which is just a little less flashy. But we'll carry on with, this is the emulator actually running. You can see EDI gets XORed, flags get set, and we can exit with X. And then PE, which would be running a static binary without IDA, without having to disassemble it and executing from whichever part you want in it, and it gets parsed and everything like that. So automatically maps the code and data to proper addresses based on what's in the PE file. And, since Python is at least for the most part, cross-platform. You could use this on a Linux machine or things of that nature, as long as you have PE file. This is our setup and instantiation. And you'll see this is the whole thing. This is the whole script. So it'll just take in the executable to use, the address you want to start emulating at, and what it's going to do is basically print out all the instructions that got executed. So similar to the PyDebug one, maps the addresses, loads the sections, and then emulates through for our step count. And like I said, these are examples of just the bare bones way to use these different environments. So you can definitely expand on this. And here's the 3 different examples I have that correlate more to our problems in reverse engineering. This first one is tracking memory access. You know, often a reverse engineer needs to know what exactly is going on in a function. I want to know when memory writes happen. I want to know when memory is read. I want to know if it's our memory that's being read or our memory that's being write to. You know, vulnerability research, this is pretty large. You have a string in memory. You want to see if anything ever touches that string. You would want to do something like this. And what we'll do is use a memory handler to trap access to segments of memory and whatnot and get notified. And you'll see that, you also get provided the address, what is at that memory location, and whether it's a reader or write. So to do that, I set up a memory handler, set register, set a handler, and then I'll execute. You can see I use a start and an end. And when it's actually ran in the IDA, you'll see that our memory access handler gets hit when memory is touched. And you can make it a little more specific using stack or the heap versions. But as an example, I just used the memory access one. And if you'll notice, there's the first argument on the printout at the bottom is the address, and then what's at that address, the size of the request, and whether it's a reader or write. Path enumeration, when we talked about complex code paths, we talked about needing to go from point A to point B or figure out why a process can't get to a certain basic block. And with that, you can use something like this. It's a simple example of logging the branch logic used and what data is being compared in that branch. So we'll set a mnemonic handler to hook compare. And since our handler receives the values, we can get an idea of what exactly is going on in this function or this piece of code. And it's potentially time saving when looking at 100 node functions or, a large piece of data. And what we'll see is, as we've seen before, except this time we're going to set some stack variables to our values, and then we'll set a handler and execute. And you can see right here, there's 2 compares hit. Both of them get hit. We can see what was in operand 1 and what was in operand 2. And the second one, you can see it was being compared to 2. So it could be very useful for finding different code paths, especially in a live debugging way, and certainly in IDA if you can set up the memory and the values properly. So the third one is return value enumeration. This will exercise a function with varying arguments, and it will record the return values. This could be you could script this to do brute force of a function to figure out what's going on. You could force it to build a data set of exactly what the return value will be and things of that nature. So I don't know if you can see